Black holes are among the most fascinating and mysterious phenomena in the universe. They are enormous entities in terms of power, yet almost undetectable to us. For instance, a black hole with a mass 2 to 4 million times that of the Sun is beyond our direct perception. Over the past few decades, research has dramatically increased our understanding of these cosmic objects. We've gone from knowing almost nothing about them to uncovering more and more as technology advances. Recently, Michio Kaku announced that we've finally been able to look inside a black hole, providing new insights that could reveal details the scientific community missed before. Before diving into Kaku's discovery, it's important to understand the basics of black holes. Although most of us have heard of them, there are still many gaps in our knowledge. In 1916, Albert Einstein published his theory of general relativity, which predicted the existence of black holes. At that time, black holes were purely theoretical, and it took another 50 years for scientists to find evidence proving their existence. In the 1960s, researchers studying the Cygnus constellation observed a strange blue star emitting X-rays. This star wasn't an ordinary object but was orbiting a massive, dark entity. Upon closer inspection, it was found that the X-rays weren't just moving freely but were being sucked into this dark object. This was the first clue that black holes were real. The object was named Cygnus X1, located 6,000 light-years from Earth. It was brighter than the Sun and incredibly dense, with a strong gravitational pull. This gravitational force was so intense that not even light could escape, hence the name black hole. The discovery of Cygnus X1 was groundbreaking because it confirmed that black holes were not just a figment of Einstein's imagination, but real phenomena in space. This revelation spurred scientists worldwide to investigate further, leading to the discovery that there may be over 100 million black holes in the Milky Way alone. However, due to their elusive nature, we still don't have an exact count, but it's believed that there are millions of them in our galaxy and universe. The most striking characteristic of black holes is their gravity. Their gravitational pull is so intense that anything that enters a black hole is crushed down to a singularity. To simplify, black holes can be thought of as gigantic vacuum cleaners that suck everything in. One of the most terrifying aspects of black holes is that if someone were to fall into one, they would eventually be stretched into a long, thin shape as they approach the singularity. This process would occur slowly, with the individual likely dying before reaching the final point of no return. Despite the danger they pose, black holes remain a subject of intense study. The closest known black hole to Earth is located 500 to 1,000 light-years away, which raises questions about whether we are in any immediate danger. In 2021, scientists captured the first clear image of a black hole, specifically the M87 black hole. This image was taken over several nights, and each photograph provided more evidence about the black hole. The researchers were able to combine the images to form a more complete picture, revealing that black holes have 3 layers, not just a single void of nothingness as many people assume. The first layer is called the event horizon, the point of no return. Once something crosses this boundary, it's pulled into the black hole and can never escape. The second layer is the photon sphere, where light can orbit the black hole but cannot escape. The third and final layer is the singularity, where everything that falls into the black hole is compressed to an infinitely small point. At this point, the laws of physics as we understand them break down, and what happens beyond this point remains a mystery. What makes the study of black holes even more challenging is that no 2 black holes are the same. While they generally follow the same 3-layer structure, their specific properties can vary drastically. Researchers can study black holes indirectly by observing the radiation they emit and the gas and dust surrounding them. However, sending a probe inside a black hole is impossible, as anything that crosses the event horizon is crushed into the singularity. This presents a significant obstacle for scientists, as traditional methods of scientific inquiry do not apply to the study of black holes. Nevertheless, many theories exist regarding the formation of black holes. One of the most widely accepted is that black holes are created when massive stars run out of fuel. Once a star can no longer produce enough energy to counteract gravity, it collapses inward, potentially forming a black hole. Despite the challenges, scientists continue to make strides in understanding black holes, and the recent discovery by Michio Kaku offers even more tantalizing clues about what might lie inside them. As a star continues to burn, it begins to collapse in on itself, becoming denser. If the star is massive enough, this process can continue until it forms a singularity. To understand the nature of black holes, NASA researchers focused on the center of the galaxy M87. Astronomers observed a powerful whirlpool of extremely hot hydrogen gas spinning at an incredible speed of 1.2 million miles per hour. The immense force of this rotating gas should have caused it to fly apart, but it didn't. Researchers concluded that there must be an enormous mass at the center of the galaxy preventing this from happening. This mass was estimated to be 2 to 3 billion times the mass of the Sun, and it had to be a black hole. However, black holes don't just follow one theory. In 1963, New Zealand mathematician Roy Kerr applied Einstein's theory of gravity to describe rotating black holes. Kerr's model showed that a rotating black hole would not collapse into a point, as previously thought, but instead into a ring of fire or a thin disk. The speed at which this disk spins would generate radial forces that prevent it from imploding. This rotating disk of matter is known as the ergosphere, an area around the black hole where the laws of physics begin to break down. What makes Kerr's theory particularly fascinating is that it predicted the existence of an Einstein-Rosen bridge, also known as a wormhole. A wormhole is a theoretical passage through spacetime that could connect two different regions of the universe or even two parallel universes. The idea suggests that if you were to fall into a black hole instead of being crushed, you might be sucked down into a tunnel and emerge through a white hole in another universe. To understand how this could work, we need to examine spacetime, as described by Einstein's theory of relativity. Spacetime is like the fabric of the universe, where objects with mass bend this fabric, creating a gravitational field that causes other objects to move toward them. Now, imagine a piece of paper representing spacetime. If you place 2 points on the paper and draw a line between them, it shows how objects move through spacetime. But what if you could fold the paper so that the 2 points are connected by a shortcut? This is the basic concept of a wormhole, an instant pathway through spacetime that connects distant points. Wormholes are not just a science fiction idea. They are a direct prediction of general relativity. Although no one has observed one directly, the reason for this is that wormholes are inherently unstable and would collapse almost immediately. The existence of an Einstein-Rosen bridge implies that black holes might not just be cosmic vacuum cleaners but also gateways to other regions of spacetime. Could we use a wormhole to travel through space and time? Unfortunately, the answer is likely no, at least not in the way we imagine. Even if we could stabilize a wormhole, it would not allow for faster-than-light travel. Einstein's theory of special relativity sets the speed of light as a fundamental limit on how fast anything can travel through spacetime. However, the idea of wormholes and black holes as potential pathways to distant parts of the universe or even to different times has been a topic of speculation among physicists for many years. If we could figure out how to achieve such travel, it would revolutionize our understanding of the cosmos. One of the most intriguing concepts in this area of study is the Kerr wormhole, named after mathematician Roy Kerr, who first described it using Einstein's equations of gravity. A Kerr wormhole is essentially a theoretical tunnel through spacetime that could connect two distant points, such as two different universes or two different times within the same universe. This wormhole is often envisioned as a ring-shaped doorway. In the story of Alice in Wonderland, Alice steps through the looking glass to enter a world where logic and reason don't always apply. Similarly, passing through a Kerr wormhole could potentially transport a traveler to another universe or a different time where the laws of physics might be vastly different from what we know. While the potential for wormholes to enable interstellar travel or time travel is exciting, it remains a subject of debate among physicists. Some argue that wormholes, particularly Kerr wormholes, may be unstable or impossible to navigate due to intense radiation and subatomic forces surrounding their entrances. Critics also point out that Einstein's equations of gravity, which are used to describe wormholes and black holes, only account for gravity, not the quantum forces that govern radiation and subatomic particles. To truly understand these phenomena, a new theory is needed, one that combines the laws of gravity with a quantum theory of radiation. This is what scientists refer to as a theory of everything, a unified theory that could merge both Einstein's theory of gravity and quantum mechanics. One promising candidate for a theory of everything is string theory. String theory posits that the fundamental particles of nature are not point-like objects but rather tiny vibrating strings. These strings give rise to different particles, with each type of particle corresponding to a different vibrational pattern. An intriguing aspect of string theory is that, as these strings move through time, they warp the fabric of spacetime around them, creating phenomena such as black holes and wormholes. In this way, string theory not only unifies gravity and quantum mechanics but also provides explanations for many of the mysterious phenomena we observe in the universe. However, string theory introduces a complication that challenges our understanding. It requires 10 dimensions of spacetime for the strings to vibrate, far more than the 3 dimensions of space and 1 dimension of time that we experience in our everyday lives. While it's difficult to imagine what these extra dimensions might look like, physicists have developed theoretical models to help us visualize them. Consider a 2-dimensional lake inhabited by fish that are only aware of length and width. To these fish, there is no concept of height, and they cannot even fathom what it might be like to live in a 3-dimensional world. Similarly, the extra dimensions required by string theory are beyond our direct experience, but they offer a new way to understand the universe.